if anybody else forgot, what we're going to be doing is, so this one, again, we're going to want to show geometrically. But what I'll look at is, again, to also remember that this is the form, Courtney, of a vector is what we call the linear combination. We could also, if you prefer, just write it in component form. OK? So it's the same thing. All right, Courtney, how we have that. So it's the exact same thing. So what I'm going to do is I'm going to graph u. And then I'm going to apply our new vector, or I'm applying my operations for my new vector, which is a scalar. So let's just graph what u would look like. OK? So remember, this is 2I minus j. It's going to be the same thing as going over 2 minus 1. So that is my vector u. But that's not what they're asking us to go and graph. They want us to graph v. Well, v is 2/3 of our scalar u. So remember, when we had a scalar, that means a number that was outside our vector, we applied that scalar to both of those coordinates. So therefore, v equals 2/3 2, comma, -1. Distribute. Yes? Huh? Oh, it's 3/2 instead of 2/3? OK. That'd make more sense. Thank you. Let's do it that way. So if I did 3/2, then that would become 3. And this would become a -3/2. Does everybody see that, what I did? I just multiplied the 3/2 times both of the terms. 3/2 times 2 is 3. 3/2 times -1 is a -3/2. So now let's go and graph v. So v now says go over 3. So now I'm going to go over 3. 1, 2, 3. And then now I'm going to go down -3/2, which is like -1.5, right? So go over 3, and then down 1.5. And what I want you guys to see is what the scalar does. Remember, the scalar is going to affect its magnitude. It does not affect the direction, right? Notice how this is still on the same vector, but what the scalar does is either elongate it or reduce that magnitude of the vector, where the magnitude is the length. That was number 41. Okay, so when you're dealing with vectors, that's going to affect the magnitude of your vector, not affect the direction, which we're going to talk about next in class.